Okay, today we want to explain how activation-induced cytokine deaminase, or AID, regulates survival of germinal center B cells. And to understand this, this is a complicated, to understand the paradox here, I'll explain the paradox. The paradox is if you have no AID and AID dominant negative, or AID knockout mice, the germinal centers are very big, and there's a decreased apoptosis. That's with no AID. If you have too much AID, as in BXD2 mice, also the germinal centers are very big, and there's relatively low apoptosis. So how can you explain the low AID with low apoptosis and high AID, also low apoptosis and big germinal centers? The key is to realize that they're not the same process. AID, activation-induced cytokine deaminase, does the one thing, and that is it induces these double-stranded breaks so B cells can be arranged. It also can cause these same breaks in tumor cells, and then they'll undergo DNA damage and repair or apoptosis. So that's what AID does. That's what most people focus on. That's why the problem comes up. But however, B cells uniquely have a survival mechanism that's independent of AID, and in fact it needs AID to promote their rearrangement and somatic hypermutation, rearrange the B cell receptor that delivers another survival signal that's not available to cells that are just simply undergoing DNA damage. So this is the key thing. So if you look here, I sort of drew this these curves. What we call a DNA damage survival curve is very high. They get with AID plotted here in the x-axis is 0. AID DNA damage survival is very high because there is no DNA damage. AID is 0. And as you increase AID, DNA damage survival goes down because now we're having DNA damage. Of course, we have repair, but nevertheless, there's going to be some loss of survival because there will be DNA damage. The next important thing to realize is, what is the shape of this curve? Well, a little bit of AID causes a fair amount of damage, but more AID past the normal amount doesn't cause increased amounts of DNA damage that can't be repaired. So it flattens out. And I'll get to that in a second because we measured this, what happens with normal AID, high AID in BXD2, and what happens when you renormalize it. It doesn't affect DNA damage. So this is what most people think about. They always focus on DNA damage, and that's why they come up with the sort of this paradox of big germinal centers and high survival, even if no AID. Now, what does AID do? Let's look at the other curve. There's another process of B cell selection, and I'm going to call that over here. You see, DNA survival versus selection survival. For B cells, unlike any other cell in the body, they actually have to have some AID to cause somatic hypermutation so they can get a survival signal based on affinity of IgG binding to its receptor that started this whole process. Binding to the antigen that started the whole process. So this is what the AID survival curve looks like. This is for B cells. No AID, they're not going to survive very well because the B cell receptor won't undergo any somatic rearrangement. But as you increase AID, they'll actually get more and more affinity maturation, better signaling through the B cell receptor as the B cell matures, and they'll be able to survive. And then it'll go up. And at some point, of course, we know that too strong a survival, this is another immunologic thing, but strong B cell signaling can cause apoptosis. That's even yet a third mechanism. We're just worried about these two counteracting curves of DNA damage survival, which decreases with AID, but and B cell survival, I should say selection survival, which increases with AID. Now, so going to this model here, AID does, a lot of people might think of this, the first part, DNA damage survival. AID causes double-stranded breaks, so forth and so on. DNA damage and repair, that balance leads to apoptosis. So this is the part that people think about. They don't understand, well, how could high AID going lower, how can that lead to, how does that affect survival? But this is this. But if you throw this into with this pathway, DNA damage and double-stranded breaks, somatic hypermutation is a result of that. That increases the affinity of the B cell. and that causes the second suppression of apoptosis. This second suppressive factor in apoptosis in B cells that's due to SHM and binding of the B cell receptor to its antigen. This does not exist in like cancer cells or normal cells that undergo activation due to cell death. Now, how do we know this is right? Well, one thing is, what are the predictions for the apoptosis pathways? DNA damage and repair, if that is the apoptosis mechanism, DNA damage survival is a problem, you'll get a different set of genes. You get, P53 involved, and XRCC2 and XRCC4 and P53. And you read about this. There's papers out there that XRCC2 regulates AID survival. That's true if you just consider DNA damage. But if you consider affinity survival, or I guess I'm calling it selection survival, then it's a second mechanism to suppress apoptosis. So you'll be able to make a little more damage and still have suppression of apoptosis. And what's the pathway here? Well, we know what they might be. There are B cell pathways. There's CD40 signaling pathways, BAF perhaps signaling pathways. And I drew up here the one molecule we measured is caspase-9 is increased. Or I should say if we lower AID, caspase-9 is also is increased, right? Caspase-9 is increased. Okay. So actually we're lowering selection survival here, and so they're dying more. That's the thing. Even though you lower AID, you say, wait a minute, you're going to have less DNA damage, you got to survive more. No, you're also lowering selection survival, and that is going down at this point in the curve, and it's the mechanism molecularly because caspase-9 is the one thing we found. You say, well, wait a minute, what about DNA damage survival? We looked at that. DNA damage survival is you slide AID down from super high levels in BXD2 down to its normal level, and you look at DNA damage pathways. We looked at this XRCC4, and we looked at DNA damage and repair genes. Those are not significantly altered in BXD2 compared to BXD2 AID dominant negative. So that explains the paradox. So as I say up here, which is a little bit of a mouthful, knockout versus normal. In a normal mouse, you have to have, in a knockout, an AID knockout, there's high survival, big germinal centers, because there's no DNA damage. So there's high DNA damage survival. And selection is irrelevant. There's no selection survival. But there's so little DNA damage, there's a whole bunch of DNA damage survival. So the germinal centers are big. Notice that's not relevant to understanding the real function of AID, right? Because you need AID, you need selection survival for B cells. So that's why this is not a good thing this doesn't give much insights. Of course, no DNA damage, there's no apoptosis is low. Now, if you go to autoimmune versus normal, on the other hand, autoimmune versus normal, you have increased, in the autoimmune situation, you have increased survival based on selection. You have high selection survival. And, we don't know the only thing we know is caspase-9 is a little bit lower here than here. So somehow you'd say selections, but we have to look at this. As FC, this implies FC receptor signaling, and that's selection survival. We're down to this model where, it must downregulate caspase-9. We have to look at that pathway, what mechanisms of survival are. But in any event, if you slide that down and inhibit AID from making these autoantibodies, which admittedly we're not sure whether they're high affinity, but so something needs to be looked at here too. But in any event, you slide it down, you decrease selection survival, and notice you don't change this, so DNA damage survival becomes irrelevant.